MSC, multi-stage caster-aware control framework with uncertainty-aware pinch and rel-based execution layer. This study presents a control framework to mitigate the adverse effects of caster wheel misalignment on the locomotion of industrial AMRs and AFLs. Even under simple forward and backward commands, caster wheel misalignment causes severe oscillations in the measured angular velocity. Caster wheel misalignment generates resistive torque, degrading angular velocity tracking and overall tracking accuracy. To address caster misalignment, we propose a MSC framework that accounts for caster effects at both the high and low levels. Our framework first feeds the high-level CU-MPC with the estimated and predicted caster states, along with the robot's speed and position. In CU-MPC, the optimization problem is solved by an ICLOR solver to minimize the cost in 2 and 3. Here, the predicted caster state and the uncertainty standard deviation in 4 are combined into a single risk scale for 5. This risk scaler is used to schedule the cost weights for caster misalignment through 6-8, yielding the final caster cost in 9. Under high uncertainty, especially during low speed and place rotation where caster measurement is difficult, this risk term reduces the caster-based cost and prevents the IPST from optimizing in the wrong direction. The CU-MPC velocity command is encoded into a latent vector through the history buffer and GRU, then mapped by the actor to caster where wheel speed. The latent vector is decoded to predict the caster yaw angle and rolling velocity over the next 8 steps, with uncertainty represented as standard deviation in the observation vector. For CU-MPC, using GT data from ISAC-SIM and privileged information, we train an rel-based execution layer for joint caster state estimation, prediction, and caster-aware velocity conversion. This video shows simulation results in ISAC-SIM along M, S, and C-shaped paths. Simulation results in ISAC-SIM show that MSC reduces caster state estimation error and misalignment, while improving angular velocity tracking and path tracking performance across MSC trajectories. This video shows a real-world experiment on a C-shaped path. A map was built in advance using cartographer. Odometry was estimated by app using wheel encoder and data, and localization was refined with MCOL during autonomous navigation. In real robot experiments, the proposed method achieved the lowest angular velocity tracking, improved caster angle estimation, and yielded the smallest misalignment error 0.0849 radians. Overall, the proposed MSC framework addresses caster effects at both the high and low levels, reducing misalignment and velocity tracking errors to improve motion performance.